Thank you very much. It's a great pleasure to be here. Good morning, everyone, and a warm welcome. So I will talk about unlocking the future with quantum computing. At IBM Research, IBM Quantum, we work already for quite some time at quantum computing, and our work is really to unlock the future with quantum computing and develop the future of computing. Our focus mission is to bring useful quantum computing to the world. At IBM Research, we already work for a long time at quantum information theory and at quantum computing. And this work has actually culminated in 2016 by building the first 5-qubit processor and bring this quantum processor to the cloud and make it available to everyone. And I think we all can say that this really already provided a strong momentum to the community and built up the community. Since then, we have achieved quite a lot of milestones, and we have brought quantum computing from the lab to the fab. You see here a few examples. I don't want to go in all the details, but in principle, we are building up the entire stack of quantum computing, which starts, of course, with the hardware, with the qubits, the quantum processor, the control electronic. It goes second to building up the software stack to make more and more features and capabilities available through the stack, and also provide easiness and speed to program quantum computers, and of course then also third, to build up and to work on quantum applications that we in the end can also harness the benefits of quantum computing. As I mentioned, we have moved this from the lab to the fab, and I think what I want to show here is the IBM Quantum System 2. We have built the first IBM Quantum System 1 in 2019, and from this system we have learned quite a bit, which then culminated last year, at the end of year, in building the System 2. And this system is built for stability, it's built also for modularity, that we can easily and scale up the systems. I'm sure you're all familiar with quantum computing, though I just wanted to iterate a bit. Quantum computing, as we all know, is fundamentally different to classical computing. It's based on the laws of quantum mechanics, and it has a potential to solve problems which are intractable to classical computing, or solve it at faster speed, with better accuracy, and also at less energy consumption. So there are several applications we are looking into, like simulating nature, data with structure, but also non-exponential speedup. The sampling of problems, optimization, and risk analysis and option pricing. For all of this to be used by us, it's important that the quantum computers, we continuously increase the performance. And also on this we have worked quite a bit. It's first also about defining how we measure performance. And we are continuously working on this, but the importance for the user here is in the performance is to have scale, to have quality of the calculation, which is measured in circuit fidelity or also error per layered gate, and of course also the speed, which is measured in circuit execution speed. Over the time, we have demonstrated quite a few processors. I mentioned the 5-qubit in 2016, and then in 2019 we started with the theories, like what you see here is the 27-qubit Falcon, which utilized the heavy hex, or we defined the heavy hex structure, which we use for our qubit layout. Then in 2020, the Hummingbird, which where we demonstrated 65 qubits, and we demonstrated also the multiplexing of the readout. Then the year after, Eagle, which was quite a big breakthrough because it was the first chip with where we broke the 100-qubit barrier. We demonstrated 127 qubits. And why is it difficult? Because you need a packaging. You can no longer kind of connect all the 100 qubits within one plane, so you need to go 3D. And this is quite an effort to build like a package which also works at low temperature. This we made possible. And then we could further scale to the 433 qubit in 2022 with increased signal density. There's a lot of development also in the control and in the cabling in order to put everything into the fridge. And then last year, end of the year, we demonstrated Condor with all the first with more than 1,000 qubits, where we demonstrated the scale and the yield of building a quantum processor. So with this chip, it was really about pushing the limits of scale and yield. It's also increasing in size, as you can imagine if you look at the pictures. And of this series of quantum processors, we learned a lot also about the qubits and how we can further improve. And based on this knowledge, we also demonstrated then at the end of last year the so-called Heron chip. And Heron is using tunable gate couplers for connecting the quantum bits. And this has several advantages because you can increase the fidelity and you can increase the quality and the speed of the chip. So with this chip, Heron, which is a 133 qubit chip, we demonstrated much higher quality, much higher speed, and it also provides us the modularity which we need in order to further scale up the number of qubits in the future. You see here kind of a 3D animation of the chip. You see the different layers which are in this package. You have the qubit layer, you have the resonator layer, you have the substrate through vias. And with this chip, we could, as I mentioned, demonstrate kind of almost negligible crosstalk between the qubits, which is very important, and also a much higher quality by reduced gate error and much higher speed, which is critical if you want to increase the depths, of course, of the calculations you can do. So now looking at the quality, and this is, of course, this is a measure of the quality. I brought here a demonstration and a measure of the error per layered gate, which is a fidelity measurement of the Eagle chip with the 127 qubit chip, which we used before, and also the Heron in comparison. And of course, there's also a timeline, kind of the Washington and these chips, which are in the square. They were in the range of about 22 to 23. And you see on this logarithmic scale that we continuously improve the quality of these quantum processors. And you also see very nicely that we could improve the quality with introducing of the Heron chip. And I'm not sure whether this works, but let's try. Yes, it works. So these are all Eagle chips with 127 qubits, and this is a Heron chip with a tunable gate coupler, where you see a jump in the quality. And this is where we are currently working on to further improve also for the EPLG with 100 gate operations, 2-qubit gate operations, and this is currently in making to reduce this to below 1%. So you see a lot of things are going on, and the nice thing, what you see here also with the hardware which we develop, you have continuously improving error rates of our system, which also provides to the user increased quality and thus, of course, also increased potential to demonstrate nice calculations. The scaling is critical because in scaling, we increase the complexity of the problems we can solve in the future. And how do you scale? You can't make the chips infinitely big. So you need to come up with a modular approach. And this modular approach we have started to implement already last year, where we demonstrated and connected also already quantum processors like Herons. And this year what we want to demonstrate that we will have a quantum bus. So they were connected by classical bus. This means you can do a quantum operation on each of the processors. But with a quantum bus, you can then also do quantum operation across the different processors. So scaling through modularity is really an approach and a vision which we are implementing not only on the system 2, which I've shown you, which we can expand also with the electronics and the cooling system, but also with the different quantum processors. So this kind of summarized is in our roadmap. And here you see a part of the roadmap, which is the hardware part at the bottom. You see there are more things coming later. You see the software layer, which we are developing to make it easy to use quantum processors and use Qiskit open source software, where we have started with the circuits, the Qiskit runtime, and if you go further up the software stack, where you work as a researcher, not needing to know the implications of the hardware, and you can then, we have developed also here different modules like the application modules, but also what we are focusing right now is really the middleware, quantum serverless, circuit knitting, different toolboxes and circuit libraries in order to make it simple to program and use quantum computers. And of course, if you go further up the stack, then you see there are also prototype quantum software functions, which we have just released, which make it then easy to use quantum computers for solving your specific problem, application problem. So this roadmap has been actually the first time released in 2021. And we are now, end of last year, expanded this roadmap. Because now we know more, we can look further into the future. And you see several things are coming up. We are actually focusing now much more on the quality and the number of operations which we can do with quantum computers. You see here the number of gate operations increases quite a bit from 5,000 to 10,000 to 15,000, and then you see actually a big jump. If you zoom in, there's a big step from 15,000 operations, gate operations you can do more than millions. And this is when error correction comes in. And that's an important milestone we want to achieve in 2029, where we bring in then error correction and fault tolerance into our roadmap and into our systems. So dealing with errors is obviously a very, very important field. And there are different ways of dealing with errors. Everyone is pursuing them. Error suppression is one of the big ones. And then error mitigation. This is something which we demonstrated already that you can utilize it. And error mitigation is in principle, you understand the error and you can then extrapolate to zero error and you don't affect your result. Though this error mitigation and being able to do this on a chip above 100 qubit allowed us to move into the era of quantum utility. Because in that era, you can start to compete on the specific problems with the largest HPC computers which we have. And so we had last year demonstrated this era of utility by a quantum computer which got in competition with a classical computer, an HPC system, and demonstrated that the quantum computer can exactly produce a result where the HPCs could not accurately produce it. They can not simulate the result anymore because you cannot simulate above 100 qubits. And then you can, of course, use approximations. But the approximations actually did not work out very well at the beginning. And I want to show you this here in the form of a plot. We did kind of 10 different experiments. So you have a certain mathematical problems. You calculate it in 10 different ways, quantum computer, and use also different classical approximations. And then you see here the plot builds up that they're all or almost all in a certain range if you look more closely. And the Eagle processor, the 127 qubit processor, actually are the blue lines, and the others are different approximations which have been used by the classical HPC community. And interestingly, that some of these results of the classical approximations came only in after they saw the quantum computing results and then improved their approximations. So you see right now we call it era of utility because we are now really kind of productively competing with each other in the quantum world and the classical world to improve both of our worlds. And of course, the speed of development is moving on in the quantum world. And these are examples, I don't want to go into detail, but these are examples which utilize already quantum processors above 100 qubits to test and to calculate different mathematical and physical problems. So error correction The results I've shown you before did not use error correction, but error mitigation. And what is coming next is, of course, error mitigation, as I showed before. But typically, you need a large polynomial overhead for the number of physical qubits you need for one error-corrected qubit. And that's a big problem. So what we have been working on in the recent years and also figure out how we can improve the error correction and find new algorithms that we need less physical qubits in order to do the error correction. And this has been published recently, where we demonstrated a new code, a new error correcting code, which reduces the number of qubits required by about 90%. So in this example, you have a 14 times improvement over the normal surface code, and you need like 288 physical qubits for 12 logical qubits. And that's a significant improvement compared to the recent technology results. So, of course, we need to integrate HPC and quantum computing and classical computing with each other. And this is a big work which we are also working together with partners across the world to figure out how we need and how we can best integrate these systems with each other to harness the opportunity of quantum computing and HPC together. So we are working and building up this quantum-centric supercomputing technology. We have recently also shown some first results and examples. And here is an example where we have collaborated with Fukaku. That's the Japanese HPC system, where we looked at a certain chemical problem and made both of these systems work very well together. Again, I don't want to go into detail, but that's a really very, very interesting world which is now expanding. The HPC community and the quantum community is working very well together. And for this, of course, we also need build up all the software layers, and therefore we work on Qiskit. We are bringing this together with the quantum GPUs, and this is in the end what you as a user need to have, all the capabilities and features implemented. And the software is very important to also harness the speed and the performance of a quantum computer. And on this, we also have recently released the 1.2 Qiskit version, which again represents a new era because a lot of components have been implemented in order to improve the overall performance for the user. It's faster in binding and transpiling. It needs from a compiler 23% fewer 2-qubit gates, and also it needs less memory usage for using the quantum computer. So the strongest ecosystem is very important to further advance quantum computing. It's a challenging technology. You see a lot of progress has happened, and now there is hardware available which can be utilized and can unlock, as said before, a lot of creativity by using quantum computers, figuring out new algorithms, finding new ways of implementing them and integrating it with HPC. And this is one of our initiatives which we also motivate and try to increase the momentum of really using the quantum computers and figuring out how to best use them. And so this is also why we start quantum data centers. I mentioned this at the beginning, but actually I'm very happy that we are able to correct this number from 1 to 2. So and we're very happy that we are actually opening soon in 2024 a data center, an IBM quantum data center in Europe, in Germany, in Ehningen. And this allows also European users to do the calculations, have the data, and do all the computation in Europe, which is very critical to also many of the industrial partners which we work with. So this is happening. Stay tuned. It's coming soon. And it allows easier access to all of you. And therefore, get ready now. Thank you.